All right, Professor Mitchell has already told you the logic behind the ratio test, so I'm just going to do some examples of using it. Again, the ratio test says this. Suppose the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is some number L. Well, if L is less than 1, we know that series converges. If L is greater than 1, we know that series diverges. And if L equals 1, we have a sad face because we can't use the ratio test. We'll have to use some other technique to answer our question. Now, if the series itself isn't an alternating series, the absolute value signs are irrelevant. The point of the absolute value signs is that we only care about the part of the series that is the term a sub n. We don't care about the term the negative 1 to the n or the negative 1 to the n plus 1 that's making it alternate. In particular, we don't have to worry about that part of the series when we're figuring out a sub n plus 1 and a sub n. Okay, so here's problem 50. The sum from n equals 1 to infinity of 5 over n factorial. We talked about factorials a while ago. Here's where they're going to come back with a vengeance. All right, so first we do some scratch work. A sub n is just this expression, 5 over n factorial. To calculate a sub n plus 1, everywhere there's an n in the original expression, I just replace it with n plus 1. So a sub n plus 1 is 5 over n plus 1 factorial. So I am finding the limit as n approaches infinity of a sub n plus 1 divided by a sub n. I'll flip and multiply. And again, I'll mention these terms are positive, so I don't need to worry about the absolute value signs. It's already positive. And the 5's cancel. And remember, when we first talked about the factorial, I tried to convince you you could always rewrite n plus 1 factorial as n plus 1 times n factorial. And if I do that here, the n factorial in the top and the n factorial in the bottom cancel. So when the dust settles, all I have is the limit as n approaches infinity of 1 over n plus 1. And as n goes to infinity, 1 over infinity goes to 0. So I got a limit. And in particular, my limit is less than 1. So this series indeed converges by using the ratio test. Let's do another example. This is problem 52. The factorial. Once again, these terms are already positive, so I don't need to worry about the absolute value signs. All right, so let's calculate a sub n and a sub n plus 1. Again, a sub n is just the term they gave you, 5 to the n over n factorial. A sub n plus 1, again, every place there's an n, just replace it with n plus 1. So this is 5 to the n plus 1 power over n plus 1 factorial. And let's simplify that before we go ahead and write out the quotient. That's 5 to the n power times 5 to the first power, because when I multiply the 5's, I can add the exponents. And as always, n plus 1 factorial is just n plus 1 times n factorial. So the ratio test says I should look at the limit as n approaches infinity of this thing, 5 to the n times 5 over n plus 1 times n factorial, divided by this thing, so I'll just flip and multiply. That'll give me n factorial over 5 to the n. So these cancel, and as n goes to infinity, 5 over infinity goes to 0, I did get a limit. My limit happens to be less than 1. So once again, this series converges. But in this case, we don't know necessarily what the sum is.